Got it? Okay. I'll begin. Dear Father, we thank you for this day. We thank you for the weekend that is soon upon us. We survived the first week. We thank you for that, Lord. Help us to glorify you what we do this day, Lord. Help us to make the most of this time we have together, Lord. In your name I pray. Amen. All right, so let me get to it. I could talk about Zn a long time. I think I'll just give you a few token comments here. So in particular, if we pick an integer, x, right, and we divide by n, then what does the division algorithm tell us? It tells us that there's a what? There's a quotient, and then there's a remainder, right? Like that. Now that's not what the division algorithm as we usually state it says what? X is equal to Qn plus R, right? So what's this say? This says that x is congruent to its remainder mod n, right? So if we can calculate mod n, we can find the remainder upon division by n, right? That's a useful calculation trick. For example, just to get us started here, if I take, and this is in the book, but I think it's worth going through together. 4 to the 119th power, I want to find the remainder after division by 7. All right. So the game to play with these kinds of, first of all, you can try putting 4 to the 119 in your calculator, but what's going to happen, you're going to need a really big screen, right? So what you want to do is to instead think of it in terms of congruence, right? So if we can say 4 to the 119th power is congruent to something, then we'll be in business, right? So the game we play is to just look at powers of 4 to start with. So 4 squared is 16, right? And 16 is congruent to 2, right? But then 4 cubed is congruent to 2 times 4, which is congruent to 1. So powers, 4 to the third mod 7 is just 1, right? So we can kind of get rid of those. But how do you get rid of those? Well, we take 4 to the 119th power, right? And we rewrite that as 4, that's 3 times 39 plus 2, right? And the reason for doing that is that so that's 4 cubed to the 39 power times 4 squared, right? This is all just integer arithmetic so far, but this is going to be congruent, right, to 1 to the 39 power times 4. Let me say it this way, different notation. 4 to the 119, the equivalence class of that is the equivalence class of this, right? But by definition, this is 4 cubed to the 39 times 4 squared. And then these are things we can do. We can say, okay, that's really 4 cubed equivalence class to the 39 power. And of course, this is 2, but that's 1. So anyway, that's 2. So long story short, the remainder of 4 to the 119 power after division by 7 is 2. So that's kind of neat. This is useful. This kind of arithmetic gets used in encryption, right? Where we play games with really large integers modulo other really large integers and somehow keep the government out of our business. Let's see here. Anyway, so another very important, I think, neat example that I will find time for and then regret later in this lecture is casting out nines. So if we have A is equal, if it has a decimal representation of dr d2 d1 d0, if this is the decimal representation of an integer, what's that mean? Algebraically, this means that a is equal to d sub r times 10 to the r plus plus d2 times 10 squared plus d1 times 10 plus d0, right? And I'm just going to show you a neat calculation. Let's simplify a bar in Z9. All right. That gives us information about the remainder of A upon division by 9, right? And so the basic fun fact to notice here is that 10 is equal to 1. Oh, wait a minute. Did I do that right? Yeah, 10 is equal to 1 in Z9, which is really neat because that tells us that 10 to the k is equal to 1 in Z9. I'm sorry, I forgot my bar. So we can calculate a bar, which is going to be, all of that. And how do we do this calculation? I really should write a few less steps here. So this just simplifies to dr times 10 bar to the r plus d2 bar times 10 squared bar. You can write considerably less and still get the same, capture the idea here. So of course all the 10s just simplify to 1, and what are we left with? The sum of the digits, right? Calculated what? Modulo 9. So from this calculation, we get a little theorem, right? Theorem, which is that A, rather, 9 divides A, what? If, I think this is if and only if actually, if and only if what? 9 divides the sum of the digits of A, right? If and only if, or we could say if and only if d bar r plus plus d1 plus d0 is equal to 0 bar in Z9. Which is another way of saying the sum of the digits, sum of the digits in the, it's understood that digits are decimal digits. Because I'm not going to belabor that. Not a computer science class. We're not worried about going digital or anything. So, and if you work in other bases, you're just weird. So, sorry, but that's how it is. You're like, but any number of digits is the same. We have to be open-minded. No, decimal. Sorry. So what this says is the sum of the digits are congruent to 9. Congruent to 0, mod 9. Then 9 is, then the number is a multiple of 9, right? So you can take something like 3,234,561 and quickly figure out, is 9 a factor of that? All you do is add the digits. 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 4, 12, 12 plus 5, 17, 17 plus 6, 23, 23 plus 1, 24. Nope, 9 is not a factor of that.
So if we were working
However, 3 is a factor of that, if you watch the help session from yesterday. Yeah.
So if we were working in base 12, we could do the same thing by casting out 11s.
Yes, in base 12 you could cast out 11s. In base 10 you could also do other things, like if you want to look at 11, if you want to check for divisibility by 11, you're going to look at the alternating sum because 11 is congruent to minus 1 mod 10. Excuse me. 10 is congruent to minus 1 mod 11. So if you look at this in mod 11, you get like plus minus plus minus plus minus because depending whether you're even or odd power, you get an alternating sum. And there's more awful things, like you could look at divisibility with respect to 8, then you'd get like powers of 2 with the digits. I mean, there's uglier versions of this, but yeah. Okay, anyway. A considerably more important thing I'm telling you right now. This is just fun, all right? We should have fun sometimes. Theorem 5 is let a and n be integers, all right, with n greater than or equal to 2, then a bar has inverse, and that's multiplicative, okay? Although you might say, well, duh, because everything has an additive inverse, so that's that'd be boring to state a theorem about additive inverses. Let a be in Zn. Let a bar be in Zn. It has an additive inverse. What's its additive inverse? Yeah, minus a bar. Yay. Anyway, then a bar has a multiplicative inverse in Zn, of course, if and only if the greatest common divisor of a and n is equal to 1, aka what? Relatively prime, right? What does it mean to have a multiplicative inverse in Zn? Well, I'll show you in the proof. How about that? So here's the proof. It's not complicated. If I can find a marker. Proof. Ah! Bad throw. Let's try again. Greatest, ooh, look at this one. GCD, if I feel good, this proof is going to be fluid. Let's see here. The greatest common divisor of a and n is 1, right? Assume that. This is true if and only if what? There exist, right? X and y in the integers such that what? Ax plus ny equals to 1, right? But that's true if and only if what? Ax is congruent to 1. Or let me use a better notation. That's true if and only if a bar, x bar is equal to 1 bar in Zn. This last thing I wrote, this means x bar is equal to a bar inverse in Zn. All right. In other words, x is the multiplicative inverse of a bar.
So the Euclidean algorithm is like multiplicative inverse.
Yeah. Yeah. So for small n, we can guess multiplicative inverses, but if you get large, cumbersome ones, the quick way to find inverses, well, relatively quick way to find inverses, is to calculate the greatest common divisor of the number you're trying to find the inverse of against the modulus. Then Bezout's theorem will reveal to you the inverse. The following are equivalent, theorem 7. The following are equivalent for n greater than or equal to 2. 1, missing a kind of important word here. Every non-zero a bar in Zn has inverse. 2, if a bar, b bar equal to 0 bar in Zn, then either a bar equals to 0 or b bar equals to 0. Bar, 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 bar. So many bars. 0, 3, n is prime. Ow. I guess I have to admit I just pinched my finger on my phone. That is something I couldn't have done with a smartphone. You guys got me there. I will admit it. Still, I love this one. Okay, so the proof of this is probably worthwhile. We'll start with 1. Assume true. Let me use non-Yoda English. Assume 1 true. Let's see here. So now, in other words, I'm assuming that every non-zero element of Zn has an inverse multiplicatively, right? Suppose that A bar, B bar is equal to 0 bar, and A bar is not equal to 0 without loss of generality. Right? What do I need to show then to prove 2 is true? Yeah, I must show that B is 0, because either one of them or the other has to be 0. So consider A bar inverse times A bar times B bar is equal to A bar inverse times 0 bar, since A bar inverse exists by 1, right? By assumption. But what does this give us? This gives us that B bar is equal to 0 bar. Done. Hence 1 implies 2. Assume 2 true. Then what are we trying to show? N is prime, right? So suppose otherwise. Suppose n is equal to AB, where 1 is less than A, comma B is less than n. In other words, n is composite. Right? It has factors which are neither 1 nor p. It's not prime. Working towards a contradiction here, right? Then what's that say? That says that 0 bar is equal to A bar, B bar, right? Where A bar, B bar are not equal to 0. What does that do?
Violates 2.
That contradicts our assumption of 2. Therefore, n is prime. So, what is that? That's 2 implies 3. What will seal the fate of this theorem? If we can show 3 implies 1, right? Then we get equivalence. Circle's complete, so to speak. So assume 3. True. N is prime, right? And what do we want to show? Every A not equal to 0 in Zn has an inverse, right? So let A bar not equal to 0 bar in Zn aha. Then what's the greatest common divisor? What's the greatest common divisor of A and N? Because N is prime, right? So prime is co-prime to any number, non-zero number, right? Aha, but then by theorem 5, it has an inverse, right?
What's theorem say?
What's theorem 6, did you ask me? I take the 5th. Let's see here. I mean, I use the 5th. Let's see here. Played the 5th. Oh, yeah. Okay, moving along. Wilson's theorem says something fascinating. What does Wilson's theorem say? It's a corollary to theorem 7. Maybe I should put it over here with theorem 7. Kind of since it's his partner in crime. Come on, marker. Corollary. If P is prime, then P minus 1 factorial is congruent to minus 1 mod P. Put that there. That was me, wasn't it? So the proof of this is really kind of neat. It's also based on an exercise which I haven't done. I'm not sure if I assigned for you guys, but the proof basically goes like this. Since P is prime, what do we know? You look at the list, 1, 2, find bars, 3 bar, P minus 1 bar. These are what? These are all invertible, right? Then the next thing is x squared thing you need to know about. If you look at the solution of x squared equals to 1 mod P, only x equals to 1 and P minus 1. Let me put a congruence here. X squared congruent to 1 only for x equals to 1 and x equal to P minus 1. So that has 2 solutions, right? What does this equation, though, mean? This means that x is self-inverse, right? In fact, in the help session yesterday, we proved that if you take n minus 1, it's, what do we prove? Oh, I forgot already. This is why I tape it. I need to go back and look. What's that? X equals n minus 1 is squares to 1, mod n. Yeah. Anyway, so this is the only thing that is its own inverse, right? So if you look at this list, if you then multiply these numbers, right? If you multiply these numbers, what has to happen is that like 3 inverse and 3 are both in there, 4 inverse and 4 are both in there. I mean, the number and its inverse cancel out every pair except for what? Except for these 2 guys. So basically, if I call this thing pi, to give it a name, then pi is just equal to 1 bar times P minus 1 bar. But that, by the way, is just minus 1 bar. Did I say pi? I guess I should say pi bar. There, is that better? I'm sorry, this is awful. But anyway, that proves that the P minus 1 factorial is congruent to minus 1 mod P. Because this is just cancellation, yeah.
Can we just, we already know that we're in Cn, can we just not write the bar? Is that?
Yes. Yes,
Are we going to start doing that?
very soon. Very, very soon. Soon. Very soon. Another thing that's worth knowing is, of course, Fermat's theorem. Fermat's theorem says that if P is a prime, then a to the P is congruent to a mod P. Well, anyway, I'm going to let you read the rest of the section. I'm going to go on at this point. But it's a very thorough review of like the most famous and important things about Zn in this section. It's very useful. And it should serve us well as we study the group structure of Zn. Well, Zn doesn't have a group structure because 0 doesn't have a multiplicative inverse. I mean, the question is what I mean by group structure of Zn. What's a group? I don't know. So in the interest of getting answers to that question, let's go on. Permutations. And also to stop writing bars and stuff. So, I mean, I don't know. I think if I was teaching Math 200, I'd probably spend, I don't know, 6, 7, 8 lectures on this material, right? I mean, a long time. It's important. So what are permutations? I want to talk to you about permutations for the remainder of today. This is section 1.4. I think what confuses people about permutations is mostly just if you run into the notation, the specialized notation for permutations without ever having it explained to you properly, it can be confusing. But if you understand what the notation means, not really that complicated what these things are. There's a certain computational difficulty with permutations that never goes away, right? But it's not really that complicated a thing. All we're saying here, so you could talk about the abstract notion of permutations. Permutations on a set S would be simply the set of bijections on the set. All right? But the permutations I'm talking about today are, we take S equal to, I call it n sub n. Nicholson is calling it big X sub n, but I'm going to keep using n sub n to mean the counting numbers up to n. So 1, 2, 3, n. Okay? So bijections on that set are called permutations. In particular, we say Sn is equal to sigma that goes from n sub n to n sub n, such that sigma is bijection. This, folks, is called the symmetric group of degree n. Degree n is, you got to be careful. You might be tempted to use the word order. That would be bad, because the order of a group is the size of a group. How many different bijections are there on n things? N factorial, right. So here's a notation we could use for that. It's kind of like case-wise defined. So we got 1, 2, 3, n. And so let's suppose that we send 1 to a sub 1. We send 2 to a sub 2. We send 3 to a sub 3. We send n to a sub n. All right? So what we have to have here is that the set a1, a2, a sub n, that has to be n sub n, perhaps written out of order, but it's a bijection, right? So it's onto. It has to hit all those n numbers. And this array or matrix notation is simply a compact notation for a case-wise defined function, which more specifically has this. Sigma of k is equal to a sub k. Now, Nicholson is really stingy with parentheses, so he'll write this in this section. Sigma k equals to a sub k, which I guess is okay. Now, so the reason for n factorial is because every one of these, your first choice, what do you got? N choices. You choose A1, 1's gone. To assign 2, there are n minus 1 numbers left. So then there's n minus 1 choices for your second thing, right? Then you got n minus 2 things left to make the third thing. Third thing, yeah. It's a third thing. And I'm sorry, it's getting to the weekend. And so forth and so on. So as you can see by counting, there are n factorial choices for the bijection. So the cardinality of Sn is equal to n factorial. But it's degree n. All right, fine, enough. Example 1, and you should leave yourself a little bit of room here because I want to add to this example. So here we're going to talk about S3, a very important example. It is the simplest non-abelian group. Sigma 1, 1, 2, 3, sigma 2, 1, 2, 3, sigma 3, 1, 2, 3, I'm just doing half of it, sigma 4, 1, 2, 3, sigma 5, 1, 2, 3, sigma 6. Yeah, I'll put that board up early, make me nervous. Who's that? Is it Dr. Wang? So there you got 6 of them because 3 factorial is 6. So you can send 1 to 1. Let me do it in a different color, actually. We can send 1 to 1, 2 to 2, 3 to 3. We could send 1 to 2, 2 to 3, 3 to 1. We could send, or you could do 3, 1, 2 for the outputs. You could do 2, 1, 3 for the outputs. You could do 3, 2, 1 for the outputs. You could do 1, 3, 2 for the outputs. Okay. Those are your distinct triples from 1, 2, 3. Yeah. Ordered triples. Now, this first permutation is actually what? We have another notation for this. This is actually 1 on what? On n3. It's the identity map on 3 numbers. Right? So in Nicholson, he uses the notation variable epsilon for that. That's his notation for the identity permutation. And it's also a degenerate notation. He uses the same symbol for the identity permutation, whether we're talking about S2, S3, S4, S5, S6, S7, S8, S9, S10. You get the idea. But that's not an unusual abuse, is it? Right? Using the same notation for the identity in different sized objects. This is a common abuse. What are the most important things to notice about the Sn? What can we say about Sn? Let's just pause to kind of smell the roses here a bit. Sn, it has, what is it? Let's say for sigma, beta, and gamma in Sn, you might notice by properties of chapter 0, sigma, beta, gamma equals to sigma, beta, gamma. Here I'm talking about associativity of composition, right? 2, sigma inverse is in Sn as well because the inverse of a bijection is a bijection, right? 3, the identity, which is of course 1 of n sub n, is an element of Sn as well. So this means that Sn forms a group because it's associative, every element has an inverse, and it has an identity. Not that we know what a group is, but I'm just saying. Okay. It's a good example. Let's do a calculation here. So we can calculate the product of permutations in the array notation. It's relatively simple. I'll illustrate the idea with some color coding here. This is the book's example, but it's not bad to go over it because I make one up, I'll somehow make it worse. So let's just be content to accept what Nicholson has given us as an example. So this is sigma. This is tau. We want to calculate the product of sigma tau. All right, so the way this is done is, you notice the first row isn't up for grabs, right? It's always 1. Starts, it's 1, 2, 3, 4 is on the top row, right? So what we do is we take this 1, right? And it goes to 4. And then 4, I'm sorry, I'm backwards. Don't. Like, that's the worst possible thing I could have just said. That is the absolute worst possible mistake I could have made. Okay, 1, top down, goes to 2. And then 2 goes to 4. So 4. Next, 2 goes to 4. But then 4 goes to 2. So 2 goes to 2. When this happens, we have that sigma tau of 2 is equal to 2. This means that 2 is fixed by the permutation sigma tau. Right? Yes?
Are you starting with tau because it's a composition?
Yes. And then next, we start with, yeah, I mean, that's the way function composition works, like that, yeah. There exist books where it's done the opposite order because function composition is done that way. Yeah, I know. But not our book. Okay, so 3 goes to 3, but that's not where it stops. It goes to 1, right? And then by process of elimination, what's the last one? 3, right? Violating my color coding, but there you go. So you notice that sigma of 1 is not equal to 1, sigma of 3 is not equal to 3, sigma of 4 is not equal to 4. So this, what we say is that the 1, 3, and 4 are moved. Did I say sigma? I meant sigma tau. I'm sorry, guys. I'm studying sigma tau right now, aren't I? Trying to multitask here. Build 2 ideas in one example for the sake of time. So I'm showing you product, but I'm also talking about fixed versus moving. So this means that the permutation sigma tau moves 1, 3, and 4. We have a notation for this. M sub sigma tau. This is the set moved by sigma tau. The set is 1, 3, 4. Okay? Let's see if you guys understand the notation. What's the set moved by the identity permutation? The empty set. What is the set moved by the permutation? Let's see here. How about this one? Sigma 2. What's the set? What's the set moved? What's M sub sigma 2?
S sub 3.
It's not S sub 3. That's the set of permutations. That's a different.
It's just N, like that.
Yep,
Sub 3, yeah.
my N sub 3 or Nicholson's X sub 3. Okay. How do you find the inverse in array notation?
Go up.
You just exactly just go up. So it's kind of silly. So if we wanted to find sigma inverse for sigma equals 2, let me make another one up. 1, 2, 3, 4, 5, and suppose we had 1 goes to 1, 2 goes to 3, 3 goes to 5, 4 goes to 4, and 5 goes to, I guess it better go to 2, otherwise I'm in trouble, huh? Then what's sigma inverse? We want to do the undo it, right? 1 goes to 1, 2 goes to 5, 3 goes to 2, 4 goes to 4, and what is it? 5 goes to 3. And you can check, using the product we discussed in example 2, that when you compose sigma and sigma inverse, you'll get back epsilon. You'll get back the identity. Here's another example. This example is kind of cute. I probably shouldn't do it, but it's too late. Let's get crazy here. Sigma 1, 2, 3, 4, 5. 4, 5, 1, 2, 3. Then tau is 1, 2, 3, 4, 5. And 3, 2, 1, 5, 4. Right. And then the problem here, this is from page 57 of Nicholson, is to find chi such that chi sigma equals to tau. How do you find such a permutation? So the
Sigma inverse and then stick it on there so it's equal to chi squared pi on both sides.
So you say what I should now do I need to compose this with sigma inverse, or do I need to, I mean, which side does sigma inverse need to go on? It matters, right?
On the right side, right?
On the right side, right? So yeah, it does not exactly, function composition does not commute, so it's important we do it in this order. chi is tau sigma inverse, which is what? That's whatever tau was, 1, 2, 3, 4, 5, 3, 2, 1, 5, 4. What's sigma inverse? Let's see here. So 1 goes to 3, reading from bottom up. 2 goes to 4. 3 goes to 5. 4 goes to 1. And 5 goes to 2. And then we can calculate the product like we did in the other example. Let's see here. 1, 2, 3, 4, 5. 1 goes to 3, 3 goes to 1. 2 goes to 4, 4 goes to 5. 3 goes to 5, 5 goes to 4. 4 goes to 1, 1 goes to 3. 5 goes to 2, 2 goes to 2. All right. This notation we will not use for the most part, but it's good to start thinking about permutations, all right? What's actually far more useful for studying problems of group theory and understanding what's going on is the cycle notation, all right? So cycle notation stems from a little bit of theory, not much. So I need a little definition. All right. Sigma and tau in Sn with the set moved by sigma intersect the set moved by tau equal to the empty set are disjoint. All right.
Yeah, these would commute, right?
Well, that's the theorem. Yeah. Thank you. What makes them interesting? They commute. Yeah. So theorem 3. If sigma and tau are disjoint. I can't spell disjoint today. Then sigma tau equal to tau sigma. Yeah. Of course, I'm talking about permutations, right? The proof is really quite beautiful. I'll do one of the cases. So there are three sets. If you look at n sub n, right? There's three things. There's like whatever's moved by sigma, there's whatever's moved by tau, and then there's everything else. So the proof basically proceeds by looking at those three different kinds of numbers and showing that in each case the maps commute their action. The easiest kind of point to see is this one, right? If k is fixed by both sigma and tau, if you look at sigma tau of k, right, it's equal to sigma of tau of k, which is equal to sigma of k because it's fixed by tau, which is equal to k because it's fixed by tau. But then you can just do the same steps in the opposite. I can't do math. Opposite order. So that shows you that sigma tau is equal to tau sigma on all elements which are fixed by both. Right? I'll let you read the proof of the other two cases. I must go on. So this brings us to what's called cycle notation. It's really bothering me not to do that proof, but I will resist. It's really bothering me. Oh, I can't stop. No, I will not. Cycles. I have problems. Let's see here, cycles. So if we have sigma of k sub I is equal to k sub I plus 1, and sigma of k sub r is equal to k1. And now this is for 1 less than or equal to I less than or equal to r minus 1. And then we have sigma of k is equal to k. This is for k not an element of k1 through kr. Then this is definition is a cycle of length r. We write k1, k2, kr to denote this permutation. So the absence of everything except for the k sub 1 through r indicates those points are fixed. And otherwise, you just read the cycle. It tells you what goes next. Now, there's a nice picture for this, like k1, k2, k3, kr. So 1 goes to 2, 2 goes to 3, 3 goes to 4, Eventually, you get over here. I guess I could put in kr minus 1. You get to there, then you get to kr, and then you get back to 1 again. So it's a cycle. I drew it clockwise. You can draw it counterclockwise, whatever. It's all good. So this is a more compact notation for permutations. And some things get much easier. In cycle notation, if you want to find the inverse of the permutation, you just write the cycle in opposite order. Other things are really neat. Any permutation can be basically written in a very particular way as a product of disjoint cycles of particular lengths. I mean, there's a unique, sort of a unique factorization result with cycle notation. You can write any permutation as a product of cycles of length 2. These are called transpositions. And if you can find a way to write the permutation as a product of an even number of transpositions, then any other decomposition in terms of transpositions still have an even number. So we can define what's called a parity of the permutation. These are the things we want to learn about cycle notation. That's where we're going. I'm not sure what I'm going to actually get to say carefully today, but just wanted to give you the lay of the land. What I think is useful to hear is to recast these in cycle notation. So in cycle notation, this is equal to 1, 2, 3. See, because what this permutation does is it sends 1 to 2, it sends 2 to 3, and it sends 3 back to 1 again. The annoying thing about cycle notation is it's a little bit ambiguous. By the way, this could also be written 2, 3, 1, and you know what? You got me. It could also be written 3, 1, 2. Let's get nuts. You could also write it 3, 1, 2, 2, 3, 2, 3, but that's just dumb. If you take any cycle of length 2 and multiply it by itself, it just reduces to epsilon. So let me erase this offending and stupid comment. All right, this one in cycle notation is, let's see here, 1 goes to 3, 3 goes to 2. So this is also a cycle of length 3. This can be also written 3, 2, 1, or 2, 1, 3, I think. Yeah. How about this one? 1 goes to 2, right? And customarily, I mean, sometimes you might see in my work from previous years or something, I might write parentheses 3, but you don't have to. It's probably better just not to. So whatever's left out is understood to be fixed. So the cycle makes manifest what's moving under the permutation. Whatever's there, if it's a single cycle, is moved. Whatever's not is not. See, in the definition, this is equal to m sub sigma. What's this one? 1, 3. Yeah, 2 is fixed. And this one? 2, 3, right. So for S3, we have the identity permutation. We have 2 cycles of length 3. And we have 3 cycles of length 1. 2, rather. I'm sorry, I'm an idiot. Length 2. These top 3 form what's called A3. A3 is the set of even permutations in S3. These are formed by a product of an even number of transpositions. Here's a thing that you can do. This is equal to, check it out, 3, 1, 3, 2, I think. Is that true? Try it out. If we send, how can we say if it's equal? Just try it out. So 1 goes to 2, right? What happens with here? 1, uh-oh, I fail. So that's not how to, can somebody here tell me, how can we rewrite 3, 1, 2, or 1, 2, 3, you pick it. Let me just focus. Rewrite this, 1, 2, 3, as a product of 2 cycles, 2 transpositions. 1, 2, oh man, 1, 2, curses, 2, 3. I think that's the trick that Nicholson gives us, right? Is that right? See, so 1 goes to 2, 1 goes to 2, very good. 2 goes to, is 2 going to 3? Well, 2 goes to 3, stays put. How about 1? 1's supposed to go to 2. 1 goes to 2. So this and this have the same action, they're the same function. So that makes this an even permutation. It's kind of confusing. Odd length cycles work out to be even permutations because they can be written as a product of an even number of transpositions. These are transpositions. Transpositions just flip 2 numbers in n sub n. How about this? So once we've done that, we can do the other one easy, right? This is what? 1, 3, 3, 2. Let's see here. 3 goes to 2. 1 goes to 3, 2, 2. Yeah. Anyway, I hope I have shown you enough about permutations that you can do the homework. If you have trouble, email me. We have a help session Tuesday. I will try to, whatever I've missed here, fill in the gaps there. But I hope that's enough to get us started. I'm going to go to chapter, what are we next to? 2, right? Chapter 2. We'll actually start talking about abstract structures next Monday. So thanks, guys. Have a great weekend. Yeah.